Okay, thanks so much for the introduction, and we're going to see if I can figure out this clicker. I can, cool. So one question we asked with this project is, what is the diversity of predicted thermally stable volatiles at the lunar poles? Two images here from LROC NAC mosaics show that both poles have areas that are quite dark. Are they cold enough to contain volatiles, and if so, what kinds? Previous work has looked at the 80 to 90 latitude range in both hemispheres. One thing we wanted to do was expand it from 60 to 90, in part because of the challenge of being able to build a spacecraft that can thermally handle a lot of these really cold temperatures. And so if there's a place that's more accessible at the lunar poles to be able to access water, that could be both scientifically and exploration-wise pretty valuable. Also, the extent of small stability regions, a corridor of 80 degrees latitude in both hemispheres was not previously very well known. And so we wanted to expand that, like I mentioned before, to find new exploration zones, but also to get a full census of where these small outliers are. Some data sets like neutrons have a very large footprint, and hydrogen from those small outliers could be contributing to that signal. And we want to be able to then forward model based on diviner predictions, potentially what neutron spectrometers could see. And then finally, LRO, as many of you all know, has been in orbit for quite some time and has a lot of really good data. And so the other impetus for relooking at all of this and reprocessing a bunch of data and taking a lot of time on the cluster here at last was that Diviner has a very extensive time record in local, both in terms of local time as well as season, as well as most of a draconic year at this point. Not a draconic year, sorry, a really substantial fraction of a lot of the different thermal variations you'd expect. And so now is the time to start looking at this. Okay, so the two methods, one is that we had to come up with what volatiles. And so what we did is we used, as we've already seen today, the Zhang and Page 2009 calculation of different stability temperatures. In this case, we are using 1 millimeter per billion years or less is the thermally stable area. This is a hard cutoff. It has gotten some critique of maximum temperature in the past, especially by Norbert Schroeghofer. If he's still online, I imagine I'll get a question about this potentially. But the reason why we pick such a tough constraint is that if we send a spacecraft to one of the zones we predict would be thermally stable for a certain volatile, and that volatile is not there, that actually tells us something about the preservation or the delivery rather than maybe our temperatures were not quite perfect. And so we looked at water, of course, sulfur species, which are a tracer of volcanic activity, organics, which are potentially a tracer of delivery from comets. And then finally, the one super volatile we're going to look at is CO2. And so shown here on the right-hand side is a chart from a review paper showing all the different types of complex organics that are predicted to be in comets with respect to water. So water's still going to dominate cometary compositions, but if we have large trace amounts of complex organics, that is a thumbprint of a comet. Now, what data set? So this is the south and north from 60 to 90 latitude in both hemispheres. These are the maximum bolometric temperatures over the course of 10 years from the Diviner data. And more details are in the publication we had earlier this year in PSJ. All this data is also online, including shape files of the maps. I'm going to show the volatiles later. So if you want to use those, please, they're on the CU Scholar repository. You can snag them and use them. Okay, so this is water from 80 to 90 south. Especially for those of you at the back, there's not huge undetected patches of surface water ice stability from thermal data. So we found most of the big ones. So we're going to zoom in a little bit. So this is from 60 to 90. And this is from 80 to 90, which is the much more familiar view to everyone. North is on the left, south is on the right. And so in the south, it's the usual suspects again. In the north, one thing I want to point out is that there are a lot of these poleward facing slopes of highly degraded craters around about 85, which is this second gradical line from the pole. And that's really interesting because those are places that LRO is going to start sampling with its new orbit in the next extended mission a lot more. And then two areas of interest I'm going to show are next are A and B in the north and south. And the reason these are areas of interest is these are some of the most equatorward predicted surface stability areas. So in the north, again, the poleward facing slope of highly degraded craters theme is coming out, but we do have small patches. Let's see if I can get the pointer to work. Maybe not. Okay, so you see small patches of places on very degraded crater rims between 85 and 80 north. There's not a whole lot outside of 80 north in the northern hemisphere in terms of surface water ice patches. But in the south, there is, shown on this right-hand panel, smaller craters inside poleward facing slopes of older craters that are stable south or north of 80 degrees south. And what's unique about these smaller patches is these are topography we don't expect to be as old. So this might actually be cold traps that are sampling different eras of volatile delivery to the poles. So please go here, it would be cool. Okay, well, it's literally cool. Anyway, I really should stop making these temperature diviner jokes. Okay, so I did mention that we were looking at different species of volatiles. So here is a little bit of a sample. So we've got sulfur, water, hydrogen, cyanide, and CO2. Left-hand side is less volatile, right-hand side is more volatile. And hydrogen cyanide was picked both because it's an organic. Also, it's something that if you want to use this water for astronauts, you really don't want your astronauts coming into contact with. And if you don't know why, it's an Agatha Christie like murder method. So we don't want astronauts in hydrogen cyanide, or we want to make sure we know they're there. So sulfur is in yellow, water is in hydrogen cyanide is in green, and CO2 is in purple. And so one thing to kind of take away is that if lunar volcanism significantly contributed to the current polar deposits based on thermal arguments, you'd expect a lot of sulfur pretty much in all of the water that you would expect. And then in some of these places, especially this poleward facing slope in the far left-hand side panel in the north, this is a highly degraded crater rim that's facing poleward. There are some areas in the north where you could sample or where you'd expect all of these things to potentially be stable. Sorry, I'm just checking on my time before Parvati reminds me. 3 minutes left. Perfect. Okay. And then in the south, again, it's the usual suspects. These are the deepest, darkest PSRs. So we're also expecting some amount of CO2. The locations match up with the Shographer et al. Work for surface CO2. Our areas are a little bit smaller though, because of that much tighter thermal constraint. And then finally, since this is the exploration forum, I'm going to pitch that Amundsen crater, which is panel C up here, is a great place to go with a future robotic mission, because the slopes driving into that PSR area where hydrogen cyanide, water, and sulfur are all predicted to be thermally stable, at least to 1 millimeter per billion years, is right against this very sharp part of the shadow in Amundsen. So you could potentially drive in over a relatively flat surface, grab your ice, and drive back out. The thermal gradient would be really high, but you wouldn't have to survive in cold for potentially very long. So Amundsen crater is a great target. Okay, and then for reference, we have talked about Viper a lot this meeting. This is the Viper landing site in red here. One thing you might notice that's different from yesterday is there isn't a whole lot of blue in this region. This is because the diviner footprint is on the order of 250 to 300 meters, which is much larger than what Viper is going to be able to access. So one thing that's going to be really interesting with Viper results and other local measurements of shadowed area is that we do expect microcold traps and other effects to really start affecting the Viper scale, but not the diviner scale. So bridging that gap is going to be really interesting when when Viper starts returning data, because then that can be our anchor point and our ground truth for the rest of these maps. Okay, conclusions. There are some really cool off-polar thermal stability areas for water ice. Both poles host locations where a variety of volatiles would be stable. On the 250 meter scale, explorations of these sites could be places where if you pulled an ice core, you could get at a record of the volatile delivered to the moon, because we'd expect everything that arrives there to stay there. And one key question, which will hopefully be updated by LPSC of next year, if not sooner, is one question we have after all this work is if there's so many extensive areas on the surface where water ice could be thermally stable, what does that mean for burial? Is the current stability regions at the surface representative of it at depth over time? And what does that mean for things like neutron measurements? So I'll thank LRO, Diviner, and Lunar Flashlight and direct you to the paper if there are any other questions.
Great. We have a comment for you from online from Norbert.
Okay.
He says, you're the first to make cold trap maps for this many chemical species, so it's perfectly fine to use the simple peak temperature criterion, and he gave you a big thumbs up.
Well, and if Norbert says I'm right, then
Then
we're good, right?
We're all good. That's all we need here.
And I think to kind of echo that point is that when we're making these predictions, it's really important to articulate what our assumptions are and what the purpose of these are. And it would be really cool to use some of Norbert's new methods for some of these volatiles as well. And I know Norbert's working on CO2 and potentially others, so we should probably chat the next time we see each other in person.